Hey, and welcome to the lecture on sp hybridization. And sp hybridization is what we're going to have to use in order to account for the bonding in something like acetylene. So in sp hybridization, we're going to take a look at the carbon. The carbon's electron configuration is 1s2, 2s2, 2p2. And we're going to switch over to an orbital diagram. So there's 1s2, and here is 2s2, and here is 2p2. And we immediately see what the problem is. So according to valence bond theory, we need to overlap two orbitals with two electrons in. And if we look at the hydrogen, of course, it has an electron configuration of 1s1. So we know that hydrogen is capable of making a bond by overlapping that circular s orbital with one of carbon's orbitals. And right off the bat, you can see, well, carbon, right, has to make four bonds. It makes a single bond here and a triple bond over here. And right now, it's only got two orbitals that are capable of bonding. So it can only make two bonds, but we need it to make four. Not only that, we can see that this angle here is going to have to be 180 degrees according to Vesper. Remember, in Vesper, right, we count the number of repulsions and a bond and a lone pair, right? We just need to count up the total number of bonds, ignoring the difference between single, triple, and double, right? We just count them all as a single thing. And we can see we've got two repulsions here. Two repulsions are going to give you that 180 degree angle, that linear geometry. You might say, well, what's the problem here? So can't this be accommodated right off the bat? And the answer is no, it can't, because those p orbitals are at 90 degrees to each other, right? So you got a p orbital that points up, say a 2px. You got another p orbital that points along the y-axis, and you got another p orbital that points along the z-axis. And these are all 90 degree angles to each other. So the difference between an x and a y and a z-axis, right, is 90 degrees. So ain't going to work with just regular p orbitals. So the normal approach, right, is to do this as a two-step problem. So we do what we call promotion. So we start off by kicking an electron from a lower energy orbital to a higher energy orbital. So we're going to take the electron out of the 2s, and we're going to promote it into a 2p. So that gives us, if you like, 2s1, 2p3, I suppose. Now you've got four orbitals that can make bonds. But again, the problem is that these are at 90 degrees to each other. And we can see in this molecule here, the bonds need to be at 180 degrees to each other. So this is where hybridization comes in. And in sp hybridization, what we're going to do is we're going to take 1 part s to 1 part p. So remember, when we write sp, we could write that as s1p1. We're taking 1 part s and 1 part p and blending them together. And those are our hybrid orbitals. So there's our 1s. It hasn't changed at all. But now we've got these hybrid orbitals, the sp hybrids, and we've got one electron in each. And those two p orbitals we haven't done anything with, and so they are still over there to the side. Now, look at this. We've got our four orbitals that can make four bonds. But the beautiful thing is if you look at the sp hybrids, so you've got an s orbital and you've got a p orbital, and you kind of blend them together. And what you get are these sp hybrids, and I'll draw these maybe in blue. And the beautiful thing is that they have the geometry that is exactly what we need in this case. One points to the right, and the other one points, there we go, in green, all the way to the left. So you've got that 180 degree geometry there. So if you're trying to understand the bonding in a molecule like this, and you've got that 180 degree linear geometry here, you need orbitals that have that 180 degree geometry, and the ones that have that are SPs.